Hi, I'm Xiaoyang, a PhD student at Rutgers University. It's my great honor to present our paper. This is a joint work with USTC and BIT. Let's see the outline of this presentation. I will introduce the background first. This paper focuses on vehicle sensing, which is to use in-vehicle sensors to collect data from traffic environment. As the image is shown, an equipped vehicle has many sensors to sense data on the road. Based on this data, many applications can be designed for driving assistance. We use a 2D table to summarize the existing world for vehicle sensing, such as the method designed based on the mobility pattern of homogeneous fleet and participatory mode. However, a common weakness of homogeneous method is the single fleet has bias on travel regions, while participatory mode requires the effort from drivers. I will address these issues based on the new opportunity. Now, many commercial vehicles are equipped with sensors and communication devices. Therefore, the new opportunity is that we can involve all commercial vehicles into sensing to achieve a higher sensing coverage with less bias on travel regions. However, this also brings a challenge, that is the duplicate sensing coverage, which may improve the cost of sensing. As the right figure shows, there are many duplicate coverage during a day. This will improve the actual cost, such as the actual data uploading feed, the actual storage and computation resources in the cloud server. This paper designs a task scaling method to address this issue. In this paper, we study the mobility pattern of heterogeneous fleets. For example, we study the coverage of each fleet as shown in the heat map figures on the right. In addition, we designed a sensing touch scaling system and evaluated a method based on real-world data. Now, we are done with the introduction part. Let's see the design part. Let's see the definition first. We design RISC as an MDP-based model and regard the commercial vehicle as the vehicle vertex and the region they visit as the region vertex. In each time slot, we build a graph based on the future locations of vehicles in the next time slot as shown in the slide, and convert the task assignment problem into the set cover problem, which tries to find a subset of vehicles to cover all regions. Therefore, in RISC, an action is a subset of vehicles that use as sensors to sense data, and the state is a vector of reminding sensing capability of vehicles. Here, the sensing capability means the number of hours a vehicle used as sensor. Given the previous setting, let me introduce the workflow of RISC. In step 1, RISC utilizes a location prediction model to predict the future location of vehicles based on the uploaded information from commercial vehicles. Given these predict locations, in step 2, RISC builds a graph for the commercial vehicles and regions. In steps 3 and 4, RISC applies the region cover algorithm to obtain a set of actions. To limit the action space for each vehicle, we obtain one action that will not use it in the current time slot to save its capability. In region cover algorithm, the vehicle has a high priority if it has more sensing capability. In step 5 and 6, RISC chooses one action and calculates the reward. Then, in the next iteration, RISC repeats this workflow. During a sequence of iteration, RISC obtains an optimal sequence of actions and uses the action of the first iteration as the task assignment for the current time slot. In the next time slot, RISC does this workflow again. Now the design is done. Let's see the evaluation. We evaluated RISC based on the data mentioned in the previous slide with many factors. Here we show some of the results. We compare RISC with a greedy-based method on the data in the CBD region of Futian district in Shenzhen. The metric is the sensing coverage, which R is the number of regions visited by commercial vehicles, and RV is the number of regions visited by excited vehicles at the current time slot. Here we can see RISC outperforms the gradient-based method in the one possible reason is the gradient-based method does not consider the sensing capability of commercial vehicles. To study the impact of sensing capability of commercial vehicles, we saw the impact on the current changing limitation of capability. We find the difference between two methods reduced, which the sensing capability increased. In summary, we studied the mobility pattern of four fleets based on the real-world data in Shenzhen, including thousands of vehicles. Based on our study, we designed a sensing task steering system to achieve higher sensing coverage with less cost. The presentation is end. Thank you.